In this chapter, we will be introducing the concept of integration. In this lesson, we're going to introduce volumes of revolution.
Hi everybody. Okay, now what we're going to do is we're going to take a look at another application of integration. This is called volumes of revolution. And I'm going to call this an intro merely because there's a lot of different ways that this can be done. And I'm just going to introduce this idea. And if I get time a little bit later on here, what I'll do is I'll produce some more videos here where I'll find volumes in a few different methods. I'll give you some options as to how to do this. But right now we're just going to introduce this idea. So now let me just take a quick moment here and let's just talk about what an integral again is doing. So let's say you've got some sort of function, I don't know, maybe it's something like this right here. And let's say we wanted to find the area underneath it, again from let's say a to b. Here's our x, here's our y, and here's some function here, y equals f of x. Okay? What we're doing when we take the integral, okay, if we're going to find the area under this curve here, okay, the area is going to equal the integral from a to b of f of x dx. Now, what this is doing, essentially, and I know we've talked about this, but what this is doing is this is creating rectangles. Okay? It's creating rectangles underneath this curve, but it's creating an infinite number of them and adding them up. But let's just kind of zoom in on one. Let's just think about what this is here. So the f of x right here, okay, if this is our function right here, our f of x gives us the height of that rectangle. That's what this is. This is the height. And the dx, okay, so here's our f of x, if you will, and then our dx is the width of it, okay? So this right here is our width. And so what we're doing with an integral is we're summing up basically the area of a whole bunch, the areas of a whole bunch of rectangles, putting them all together. And that's what creates the area, the overall area under that curve between A and B. Now, let's draw this out again. Same function here, same thing. Okay, so here's our function. Oh, that's terrible. I was hoping that would look a little bit closer, but anyway, you get the idea. Now, if you were to take and rotate this function now about the x-axis, what you're going to get is this function's going to be mirror imaged essentially right here. Okay, and this thing is going around like that. Now, so you're going to get this weird kind of a shape like that. It's got a, remember it's been rotated around, so it's circular and it's going to move in and out there. But let's talk about what has happened to that rectangle that we created here. That rectangle, if we're going to go just between A and B, here's A and then way out here, here's my B. If I just focus my attention on that rectangle just for a moment, then what happened to that rectangle is it got rotated around the x-axis as well. And what happened was we ended up creating a disc shape. Okay? It got rotated around and we ended up with a disc shape here. Now, the radius of that disc, the radius of the disc ended up being the value of the function right here. Here's my f of x. That got rotated around. That is going to be the distance from the x-axis up to the curve right there. The width, the dx here, okay, or the height I should actually say, the height of my disc, because now you got to think about it. What we've just done here is we've now got this disc here, looks something like that. This distance right here is my f of x. I'm just taking it out and putting it sideways here. What we would normally call the height, that's along the x-axis. That is actually going to be my dx. Okay? Now, when I integrated over here, I added up all of those rectangles, all of those infinite number of rectangles to get the area under the curve. Well, shouldn't I be able to add up the volume of all of these disks between A and B? Sorry, I think I said volume over here, but shouldn't I got the area here. To get the volume here, shouldn't I be able to add up all of those disks to get the volume of the overall shape here? And the answer is yes, I can. And in fact, that's exactly what the integral does here. But what I need to do is I need to be able to take my function, and instead of getting the area of the rectangle, we need to get the volume of one of those disks there. But that's actually easy to do. The volume of this disk here, okay, think about what a regular cylinder would look like. That's going to be pi r squared multiplied by the height. Now, in our particular case right here, the radius is going to be replaced by the value of the function itself. And our height, we've already seen here, is going to be just that change along the x-axis, our dx. And so now, if you want to figure out the volume of the shape that you get when you rotate that function around the x-axis between two values a and b, what we're going to do here is the volume is going to be the integral from a to b. We're still looking at between those two limits here. But now what we're going to do is we're going to take our function here and we're going to square it. That's going to become the radius of each one of those disks, multiplied by pi, and then we're going to multiply by dx. That is going to end up being the height. Now granted, we're going sideways here, but it's the height of each one of those disks. And when we integrate, that's going to add all of those disks up to give us the overall volume of that shape. Now, let's do an example here. And what I'll do is I'll do an example, let's say, of a cone, so that we already know what the volume is and we can check to make sure that what we've said here is correct. Okay, so this question says, we're going to find the volume of the shape generated when y equals x over 2 is rotated around the x-axis from x equals 0 to x equals 4. Now, probably the first thing we should do here is draw that out. What does that look like? Okay. Well, that's a terrible x-axis there, but you get the idea. X over 2 is going to look something like this. Okay. The point is, it goes through the origin. It's got a slope of 1/2. So we're going to start at x is equal to 0. Then we're going to go out here to 4. Okay. And that's going to only go up to 2. And so when I rotate that around, okay, what we're going to end up with here is a shape that's going to look something like that. Okay, so it's going to be a cone. Now I can figure out the volume of that cone without using calculus. Okay, I know that the height of my cone is going to be 4. And the radius at the base of that cone is going to be 2. And I know that the volume of a cone is going to be 1/3 pi r squared h. So it's going to be 1/3 pi 2 squared times 4. Well, 2 squared is 4, so this is going to end up being 16 pi over 3, whatever those units are. So I already know that that's the answer that I'm shooting for. So let's see what our new method here of finding the volume is going to be. So my formula here for finding the volume is going to be the integral from a to b of pi multiplied by the function squared dx. Now, in this case here, my limits of integration are going to be 0 to 4 pi. This will be x over 2 squared dx. Okay. Now, because that pi is a constant there, I can take that out. Additionally, this is going to end up being x squared over 4. So I'm going to end up with a coefficient of pi over 4, and I can just take that out front there. That's not going to cause me a problem. I can introduce that later on here, and I get x squared dx. So I'm going to take pi over 4 multiplied by the integral from 0 to 4 of x squared dx. Okay, so pi over 4. And when I take the integral of x squared, that is going to get me x cubed over 3. And I'm going to evaluate that from 0 to 4. Now, there's that 3, right? There's that 1/3 popping out. So I'm kind of glad to see that. Now, I am going to evaluate that, okay, between my two endpoints here. So this is going to be 4 cubed over 3 minus 0 cubed over 3. Okay, well, that's going to get me, okay, 4 cubed is going to be 64. So it's still going to be pi over 4 multiplied by 64 thirds. And when I simplify that 64 over 4, I get 16. So this ends up becoming 16 pi over 3, which is exactly what I had determined it to be earlier. Okay, so I'm hoping that gives you some confidence in the method that we've chosen here to determine the volume. Again, this is not the only method for coming up with volumes when we rotate, and in fact, we don't even have to rotate just around the x-axis. We can rotate around different axes, and we'll probably look at that a little bit later here. But for now, let's just take a look at a couple more examples. All right, here's another one. Find the volume of the solid produced when y equals x cubed is rotated around the x-axis from 1 to 2. And again, it's probably helpful for us to have a bit of a look at what this is going to look like. So here's our x-axis, here's our y-axis, and we know that x cubed is going to look something like that. And then we're going to rotate that shape around from 1 to 2. So it's going to be this shape right here, getting rotated around the x-axis. Now, when that's done, the shape that we're going to get is going to end up looking something like this. Coming down like that, and then, around like that. Anyway, just to give you a sense of what that's going to look like. Now, it's amazing that we're going to be able to figure out the volume of that shape. Because now think about it, prior to this point right here, no you didn't. You knew how to come up with the area of cubes, of prisms, of a sphere. But now we're going to open that up, and you're going to have the ability to come up with the volumes of some fairly complicated shapes. Okay, so now let's just take a quick look here. What's that going to look like? Well, that volume is going to be the integral, again, from a to b of pi f squared of x dx. Okay, and so now we're going to integrate this from 1 to 2. And notice we're not going right to the origin here. This is not going to be pointy. We're kind of cutting it off at the end there. Okay, so this is going to end up being pi, and this is going to be x cubed squared dx. Okay, so that's going to end up being, very quickly, the degree of this is going to jump up here. So this will be pi, the integral from 1 to 2 of x to the 6th dx. And I can pull the pi out again because that's a constant. Now let's take the integral here. That's going to end up being pi x to the 7th over 7 between 1 and 2. And so now when I plug that in to evaluate it, I'm going to get pi multiplied by 2 to the 7 over 7 minus 1 to the 7 over 7. And that basically becomes, whoops, can't see that. Well, 2 to the 7 is going to be 128 minus 1. So this is going to end up being 127 pi divided by 7. That is the exact volume of the shape that we've just generated. Okay? And that's, again, it is amazing to me that we are able to do that, and so quickly and cleanly. Let's take a look at another couple examples. All right, so this question says, find the volume of the solid generated by rotating y equals 3 to dx, okay, so an exponential, about the x-axis from 0 to 1. Okay, same thing as before. Let's take a quick look. What does this look like? Okay, so here's my x-axis, my y-axis. Well, the exponential function is going to look something like that. And we are going to take the shape going from 0 to 1. Now, truth be told, this is actually going to look very similar to the shape that we just came up with. Okay, it's going to be this circular bit, and it's going to come down, and again another little circular bit like that. So it's going to look the same here, The difference being that this is an exponential function, and so what the volume looks like at the end here is going to be a little different. Okay, and that's okay, but that's really the reason why we're taking a look at this right now. So my volume here is going to be the integral from a to b pi times the value of the function squared dx. So this will be from 0 to 1 pi of 3 to the x squared dx. Okay, so I'm going to take the pi out because once again it's just a constant. So 0 to 1, this will be 3 to the 2x dx because I've got a power of a power. I'm just going to multiply those two together. Okay, now I'm going to evaluate that. And that's going to be pi multiplied by, well, now I got to think about this. This is an exponential function, and I know that the derivative of an exponential function is the exponential function. So I know that this is going to be 3 to the 2x. Okay? But if I take the derivative of this, okay, I'm going to have to first of all multiply by the natural log of 3. Now, I don't see that in this function here. So that must mean there must be a denominator here with a natural log of 3 in it to cancel that out. Additionally, if I took the derivative of this, I would have to multiply by 2 because of the derivative of the exponent. That's the chain rule. So because I don't see this extra multiple of 2 up here, in my derivative I must be dividing by, in my original function I must be dividing by 2 to cancel that out. So now if you take the derivative of 3 to the 2x over 2 natural log of 3, I would multiply by the natural log of 3, so those cancel. I would multiply by the 2, those would cancel. It would take me right back up to that function that I see in the integral. All right, there we go. So now I'm going to evaluate this between 0 and 1. Okay, so this is going to end up being pi multiplied by 3 squared over 2 times the natural log of 3 minus 3 to the 0, which is just going to be 1, over 2 multiplied by the natural log of 3. Now, the denominators are the same there. Okay, 3 squared is 9 minus the 1 is going to be 8, so my numerator here is going to be 8 pi. And actually my denominator, I can simplify that a little bit because that coefficient of the natural log, I can bump that up to an exponent. So this is going to be over the natural log of 9. And once again, there it is. Kind of an amazing result that I can get that area so easily. Okay? Anyway, let's take a look at another slightly more complicated example before we're done. Right, so in this question, and it's going to be a little bit more complicated, but by doing this example, I'm hoping that you'll see where what you can do to work with even more complicated functions here. We're going to find the volume of the object created when the region between sine of x and cosine of x from 0 to pi over 4 is rotated about the x-axis. Now, again, let's just take a quick look. What is that going to look like? Okay, well, okay, sine of x is going to look like this. Now, remember, we're going to pi over 4. Okay, we're going to pi over 4. So if I'm just going to go to pi over 2 to start off with. And I know that pi over 2 is going to go, for sine, is going to go up to, let's say, 1. Let's go right up to there. It's going to go up to 1. So that's going to look like this. Okay, so there's my y equals sine of x. Cosine of x starts at 1 and drops down to pi over 2. Okay, and so here's y equals the cosine of x. Now, they intersect at pi over 4. So what we're going to do is we're going to take this region right here and rotate it around the x-axis. Now the result is going to be a shape. It's going to look something like this. It's going to have this little opening here. It's going to have a bit of a bubble to it, and it's going to go down like that, a little bit of a bubble to it, and then you're going to have this interior part right here. Well, it's going to be a little curved there, but it's going to be opened up. So you've got this almost like a bowl sort of a shape that's created as a result. Okay, so now this is going to be the first time we encounter a shape that's got this kind of a hole in it. Everything else that we've done thus far hasn't had that. But this is actually fairly straightforward to do. And I'm going to just draw one other little line here. I'm going to draw a little line straight down here, and I'm going to shade this part in. And that'll probably give you a sense of what we're going to do here. Okay. In order to figure out the volume of that overall shape here, what we're going to do, and I'm going to do the work below this, is we're going to take the volume underneath the cosine straight down to the x-axis, and then we're going to subtract the volume underneath the sine. Okay? So we're going to take the whole volume right here, the combined, that's what we're going to call V1, and we're going to take the green area here, V2, and subtract them, and then what we're going to be left with will be what happens when we rotate that blue portion around. In fact, maybe what I'll do, just to hopefully make this a fair bit clearer, is I'll draw red lines through there. So V1 is my red, V2 is the green, and the result is going to be the volume when we move the blue around. Okay, let's do the math here. So the volume of that first one there, that is going to be the integral from 0 to pi over 4, okay, of pi multiplied by the cosine squared of x dx. And then I am going to subtract from that the integral from 0 to pi over 4 of pi multiplied by the sine squared of x dx. Okay? Now, I can do a few things. In both cases here, I've got a common factor of pi, and I can move that to the front. But more than that, and remember back to our properties of integrals here, remember that if I had the difference between two functions here, I could split those up into two different integrals. Well, I can actually do the exact opposite here. There is a common factor of pi there. I'm going to take that out. And I'm going to put both of these underneath the same integral. So I'm going to, instead of splitting it up into two, I'm going to go backwards. I'm going to put these two together and make this the integral of cosine squared of x minus sine squared of x dx. Okay, so hopefully you'll recognize that if this was my original function here, I could have gone back to this. I could have split it up into two different integrals, and because that works, I can go backwards with that. Now, the reason why that's a benefit to me is I hope you recognize, oh my gosh, there's an identity there that's popping out. That's what makes this one fairly easy to do. That this becomes the integral of the cosine of 2x dx. That's a fairly nice expression to be working with, because I know that the integral of cosine is going to be sine. Now, when I look at this, though, you think, oh, wait a minute. If I take the derivative of this, yeah, I'll get cosine, but I would be multiplying by 2 here. So clearly something's not right there. I need to adjust for the fact that there's a 2 that would pop out as a multiple. So I'm going to divide by 2. I'm going to include a 1/2 out front there. And now I'm going to evaluate this between 0 and pi over 4. Okay, so now what have I got? I've got pi over 2 out front, and I'm now going to evaluate this between pi over 4 and 0. So this is going to be sine of 2 times pi over 4, which is going to be pi over 2, minus the sine of 2 times 0. That's just going to be 0 here. Okay, so pi over 2 multiplied by the sine of pi over 2 minus the sine of 0. Well, the sine of 0 is 0. The sine of pi over 2 is 1, so the whole bit inside brackets there just collapses to 1. Multiplied by pi over 2 is just pi over 2. So the volume of that shape way up here that we get when we rotate this around the x-axis is really simply pi over 2 units cubed. Isn't that amazing? Anyway, I hope that makes sense. I hope that you get a sense of of how we find the volumes of revolution and what we can do with even more complicated shapes. This will give you a hint as to at least one of the different strategies that we might look at later on.